The universe may be whispering secrets more loudly than we imagined. In the deepest infrared images captured by the James Webb Space Telescope, a research team from University of Missouri has identified 300 extraordinarily luminous objects from the dawn of the cosmos. Objects so bright they quite fit with what our models expect. A glimpse beyond our habits. Past generations of astronomers assumed the very earliest galaxies, forming only a few 100 million years after the Big Bang, would be small, faint, and slowly building up. But these newly found objects challenge that quiet picture. They shine with a vigor that suggests something more dramatic was happening in the young universe. If this glimpse into the early universe moved you, subscribe, like, and share, and keep journeying with us beyond the familiar stars. How they found the unusual using JWST's ultra-sensitive instruments, the near-infrared camera, UNARCM, and mid-infrared instrument, MIRI. The team scanned several deep-field regions of the sky. These instruments are tuned to detect infrared light, which is critical for seeing ancient objects whose light has been stretched, redshifted over billions of years. Among the vast sea of faint specks, about 300 objects stood out. What set them apart? They passed the so-called dropout technique test. They appear in redder wavelength images, but are absent or extremely faint in shorter wavelength, bluer bands. That signature implies the objects are very distant, and therefore seen as they were near the beginning of cosmic time. The method is elegant. Light from extremely distant objects travels for so long that it gets stretched into red and infrared wavelengths. If an object appears in red, infrared, but disappears, or is very faint in visible blue filters, it's a strong hint that the object is extremely far away, and thus very early in the universe. Why they stand out so much? Why are these 300 objects so puzzling? Because they're far brighter than we expected for such early epochs. In conventional galaxy formation theory, the first stars and galaxies slowly build up mass and light. But some of these candidates shine much brighter, and at an earlier time than predicted. If they really are early galaxies, they're telling us something is missing in our models. One co-author, Haojing Yan, remarked, "If even a few of these objects turn out to be what we think they are, our discovery could challenge current ideas about how galaxies formed in the early universe, the period when the first stars and galaxies began to take shape. What they might be, galaxies or something else. There are essentially two broad possibilities. They are truly early, massive, energetic galaxies. This would mean that tens or hundreds of millions of years after the Big Bang, some galaxies were forming stars at considerable rates, lighting up the cosmos. Such a scenario would push us to rethink how fast structure can form in the universe. They are something else entirely. Perhaps dusty, lower redshift galaxies masquerading as early ones thanks to unusual reddening. Or maybe very luminous, active galactic nuclei, AGNs, or other energetic phenomena. In other words, they may look like early galaxies, but they might not be. Importantly, many of the 300 candidates are still unconfirmed by spectroscopic redshift, the gold standard for establishing distance and age. Some preliminary work suggests a large fraction may in fact be less distant objects with extreme dust properties. Why this matters for cosmic history? If even a handful of these objects turn out to indeed be massive early galaxies, it could shift our view of how galaxies form and evolve, how fast stars could form in the early universe, and how common large structures were in the cosmic dawn era. Imagine, rather than slow, steady building blocks, galaxies could have sprinted from infancy to maturity much faster than we thought. That has knock-on effects for how we think about reionization when the first light ionized the intergalactic gas. Star formation rates, metal production, and even dark matter structure. At the same time, from a more practical viewpoint, this discovery demonstrates the sheer power of JWST to probe extremely distant and faint objects, a capability that will only grow with deeper observations and follow-up studies. The cosmos is opening up in ways we could only dream about a decade ago. 5. What comes next? The next steps are critical. Spectroscopic confirmation. Observing these objects with JWSTs, on-IR spec, or other spectrographs, to nail down their redshifts and thus their distances, ages, and spectra to reveal what's inside them. Detailed modeling, if confirmed. Revising models of early galaxy formation to account for brighter, more massive early systems. Deep field surveys and larger samples, expanding the search to more patches of sky, more objects, to understand how common such luminous early objects truly were. Exploring alternative explanations. If many turn out not to be early galaxies, what are they? Studying that will teach us about dust, obscured star formation, AGN behavior, and observational biases. One graphic summary from the University of Missouri study puts it simply: even if only a few of these objects are confirmed, they will force us to modify the existing theories of galaxy formation. The discovery of 300 mysteriously luminous objects by JWST offers one of the most tantalizing puzzles in modern astronomy. They might be the first glimpses of galaxies that formed in the universe's infancy, but grew unexpectedly large and bright. Or they might be entirely different phenomena masquerading as early galaxies. Either way, this investigation underscores how much we still don't know and how much the universe continues to surprise us. As JWST continues to scan the depths of space and time, one thing is clear: the cosmic dawn era is turning out to be far richer and more complex than we ever assumed. And these 300 luminous anomalies might be the first cracks in our assumptions.